Very good. Welcome back. Today's class will be on a new topic. We're done for the time being on about statistical mechanics. We're going to start talking about updating probabilities. So the idea here is going to be we have come up with a whole framework for discussing probability, which is as a tool for handling incomplete information. The idea there was that we are confused about what we ought to believe. We just don't know, and so we need some guidance how we ought to pick our beliefs. And we want to do it in a way that would sort of mimic what an ideally rational agent would do. But the whole thing here is that probabilities allow you to eliminate inconsistencies. And so the probabilities of different propositions are going to be assigned in such a way that obvious forms of irrationality are avoided. You're not going to be inconsistent. And that requires that your probabilities be assigned by using sum and product rules. This is how we achieve consistency in our web of beliefs. Very good. So the whole thing is that this tool was was invented to handle incomplete information. So the next step is, or rather, what if you were to get some more information? How do you update your beliefs? Let me say it differently. If probabilities are tools we use in order to handle situations of incomplete information, which is an unfortunate situation, it is quite clear that there are better probability assignments and there are worse probability assignments. How do we get to better probability assignments? If the problem was you had incomplete information, then we were morally obligated to seek more information and then to improve our beliefs, seek better and more objective probabilities. So how do we do that? That's where updating comes in. So the slogan that I like with which I like to formulate this sort of idea is that a theory of probability forces you, if the theory of probability is to be useful at all, to seek a theory for updating probabilities. This is where entropy comes in. Entropy is going to be the tool for updating probabilities. So now, several questions appear here. We had seen that one special case of updating was the use of Bayes' rule. Bayesian updating is one possibility. In this case, it was clear that you start from a prior, you add some information, and this comes in the form of data and in the form of a likelihood function. And this is what leads you to a posterior. Very good. So here we have one instance in which we are doing the updating, but we later also saw that there was another way to handle information, which was the method of maximum entropy, which allows you to include, to assign probabilities, assign probabilities on the basis of constraints. So, so here we have two interesting examples that sort of tell you what precisely we might actually mean by information. What is information? One possibility is data. Another possibility is various constraints. Uh, in fact, okay, I'm gonna say something here, and I'll probably repeat it because it's sort of like well, it's sort of true. When concepts are being like invented or designed or introduced into science, it is inevitable that there is going to be a period which sometimes lasts many decades in which the concept is still very vague and imprecise, and people are very confused. So, for example, throughout the 18th century and 19th century, particularly in the 19th century, the concept of energy was a big mess. People were all over the place with what energy was. You had theories of heat that involved things like the phlogiston or the caloric fluid. So people were really confused. The notion of a potential energy, the notion of potentials, was introduced by Laplace sometime in the 18th century, and the notion of kinetic energy is much later. It's 1820s or something like that. So people were very confused about what was going on. Potential energy, kinetic energy, heat as a form of energy, that was introduced later. Count Rumford and Mayer and Carnot and Kelvin and Joule and all of those guys. So it's an incredible many years until the notion of energy was sort of settled. It was, I think, around the 1860s or 1870 that somebody like Helmholtz was trying to understand energy better, and he came up with, he wrote a paper entitled "On the Conservation of Force." Now, that's remarkable. It means that even in the 1860s and 70s, even the notion, the term for energy was not sufficiently established. Further understanding of energy comes with Einstein, E equals mc squared, and the energy momentum tensor in general relativity, and Emmy Nether's theorems on energy is the quantity that gets conserved because of symmetry properties such as translation in time. So you see here a whole period from Newton all the way to Emmy Noether in around 1920, where the notion of energy keeps getting improved and improved and improved. Okay, same thing has happened with the notion of entropy ever since Clausius introduced it in 1960 or something, 1867, I think. And we're still working on it. So the purpose of this chapter on updating probabilities is really to contribute one more step in this invention of the concept of entropy. And indeed, one more step in this understanding of the notion of information. What is information? This may not, of course, be the last step, but this is precisely the kind of thing that you should be expecting whenever a new concept makes it into standard physics. So, what is information? Definitely data, definitely constraints. So, what we see here is that we have two methods that somehow deal with this problem. What we see immediately when we look at, say, Bayesian updating is that Bayesian updating allows you to incorporate arbitrary priors. You can pick anything you want for your prior, but the data tends to be limited to being in the form of, the information tends to be limited to being in the form of data. On the other hand, Maxent is not really a method for updating. It does not allow for arbitrary priors. It is a method for assigning. You assign a probability distribution on the basis of information in the form of constraints. So while Bayesian updating allows arbitrary priors, but it's sort of limited as to the form of information it accepts, the method of maximum entropy is very limited as to the prior you're going to have. You don't have a prior, but it is much, much more forgiving as to the types of constraints you're going to have. So what we want is a method for updating from arbitrary priors involving arbitrary, more general forms of information. That's our goal. One of the things that is actually extremely fortunate about developing a method like this is that this provides a unification, a unified theory, a unified framework. You unify Bayes and Maxent as special cases. Why is this particularly interesting? Well, if Bayes already allows you to do essentially any type of data processing you might want to do, and if physics or science in general are supposed to be based on experimentation, you can appreciate that Bayes is like really fundamental. On the other hand, if Maxent allows you to deal with more general forms of information, and that way you manage to do things like statistical mechanics, you can see that that's important too. And the moment you can bring them together, then you ought to be able to do things that you couldn't do before. In particular, what I have in mind is something like this. If you manage to take a theory like quantum mechanics, which is intrinsically probabilistic, and you manage to derive aspects of quantum mechanics purely from entropic perspectives, then the fact that you have a unified framework for handling information means that you should also be able to handle problems that are connected with experiments and the quantum measurement problem and the processing of data. So one of the things that this unified framework is going to allow us to do is to have a description of quantum mechanics that properly takes into account the problem of measurement in quantum mechanics. You might recall that in quantum mechanics we have two forms for updating the wave function. One of them is a continuous update that's given by the Schrödinger equation. And then there is another form of updating that occurs when you perform a measurement. Then you call that the wave function collapse. And that's been a serious problem in quantum mechanics because you have these two forms of wave function evolution that are completely incompatible with each other. And so it's one of the serious difficulties with the whole framework. If you have a unified framework that already allows you to do two things in a natural way, then you're making progress. So that's going to be the longer term. So now, let us continue here. When we have the maximum entropy method, we saw that there were limitations. Entropy was defined as measuring an amount of information, and that was tricky because it wasn't very obvious what you were measuring an amount of. So this led to all sorts of conceptual problems. Another problem was that it was defined, the Shannon-James entropy was defined for discrete variables. Remember how that went? You have a number of possibilities, and one of them is true, and you want to figure out which one might be true. You have incomplete information, and so you figure out a probability distribution gives you the amount of information that is missing to nail down which is the true alternative. Now, if you have to nail down one alternative among a discrete set, that's fine. That's a finite amount of information. But if you want to nail a point in a continuum, the amount of information involved is infinity, right? So the Shannon-James entropy was limited to discrete variables. Another one was that the grouping axiom was sort of reasonable, provided you didn't poke it too hard. If you start asking, really, is this an amount of expected information, or is it an amount of information? How can it be that you receive information and sometimes your distribution becomes broader? The grouping axiom was sort of reasonable, but not completely unimpeachable. So there is a question that you might ask, are there other axiomatic systems that might be used to define an entropy? How unique is the Shannon-James entropy? Well, it turns out to be the case that other people have asked exactly the same questions and have come up with other entropies. So now, if you're going to try to do inference, if you're going to try to use an entropy as a tool for reasoning with incomplete information, and you have several alternatives, how do you handle this? So you have a problem. So we need to be much, much more clearer about what it is that we want to do. The first steps in this direction, given that, well, axiomatizations of amounts of information are kind of like complicated from the very beginning, because you do not know what information is. The first steps in a better direction were taken by these guys, engineers, Shore and Johnson, around 1980. So it's been already like 40 years, a long time. And what these guys did that was actually really important is they realized that you do not have to axiomatize the concept of information. You only need to axiomatize the process of updating directly. So you can eliminate the notion of information, of amounts, of all of that. Just say, look, you want to go from a prior to a posterior. How do you do it? So this is a major step forward. Then there was another important contribution by John Skilling, and we're going to be talking much more about these guys. Shore and Johnson imposed some axioms on the process of updating, and of course people criticized them. And Skilling cleaned up their approach considerably. This was something that occurred 1988 to 1990. Those are the papers that I find particularly appealing. Um, and Several other people cleaned these things up further and further. Caesar, this was 1991, 2008, and so on. And of course, these things have been going on for a long while. My own research has been involved in very much in this direction, starting around maybe in the 1990s, 94. That's when I started doing some of this stuff here. So what emerges from all of this is the use of relative entropy as a tool for updating probabilities. This is work that's still in progress, okay, in the sense that although theories today are much, much better than theories were in the year 2000 and much better than they were in the year 1990, there is no consensus yet that we are finished with this problem. I happen to think that we're essentially done. But hey, it's still a matter of controversy. Very good. So in coming up with this, and so one of the things we're gonna do is try to derive a concept of entropy, of relative entropy, as a tool for updating probabilities. And one of the things that we're going to do that's completely different from the way that people normally do things in physics is the following. Typically, the way theories in physics have been developed, you start from a sort of mathematical formulation of your theory, and then you try to figure out what the various concepts in this mathematical theory, the various quantities that appear in this mathematical theory might actually mean. One example might be F equals ma, Newton's F equals ma. He wrote down his differential equations. They seem to be working fine. And then you start asking things. What on earth is F? What do you mean by force? What do you mean by a force that acts at a distance? So you start to really nail down the problem that you may have interpretation problems, right? When you really try to figure out the meaning of these concepts. Another one was the concept of probabilities. What do you mean by probability? Is it a frequency? Is it a measure in some set? Is it a degree of belief? How do you interpret, even when you have the mathematics under control, how do you interpret it? Another issue would be the issue of what's entropy, right? That's what we're tackling here. Yet another one would be the issue of what do wave functions mean? We have the Schrodinger equation. What does a wave function mean? So typically, the process has been you nail down what the mathematics is, and then you try to append an interpretation. What we want to do here is to follow a different process in which we start from the interpretation. So start from a clear idea of the subject matter and we and purposes and the goals and purposes of what it is you want to achieve, and then develop the mathematical framework. It's backwards, okay? the great advantage of this is because you started with a clear idea of what you wanted to accomplish, the subject matter, what you're talking about, and what the purposes of the theory is. So the question of interpretation is nailed from the start. If you were misguided about what interpretation was, then you're going to go haywire and your theory is going to be rubbish. But it will become very clear that your theory is rubbish because you never got to a good mathematical formalism, right? So on the other hand, if you start with these clear ideas and you succeed in building a mathematical formalism that you can actually compare to experiment, you know you're in the right, you're moving in the right direction. Very good. So how do we handle this? So what we're going to do is first start by asking the crucial question: what is information? This is a question that has received many answers. There is, for example, the Shannon-Jaynes version of the Shannon entropy. Sometimes it's called the Shannon information. Let's see. What is it that I want to do? So many meanings. One is Shannon. Just people call whatever you measure by this, whatever is measured by this, you call that information. Now this is a peculiarly bad feature of this, is that this is measuring really an amount of information. So we are confusing information with amount of information. It's also particularly challenging, or it's a particularly unpleasant feature of this notion of information, that it has absolutely nothing to do with meaning, with semantics, with you're only concerned with the amount, but you're not concerned with what are the significance or well, the meaning of the information that's being conveyed. There is another form of information that's associated to the notion of complexity that we're not going to discuss: algorithmic information. This is associated to the names of people like Kolmogorov and Chaitin, and it's very much a form of information or a concept of information that's favored by people in computer science. It has to do with the complexity of a sequence of zeros and ones. We're not going to talk about it. There may be some connection to the stuff that we're going to be doing, because of course at some point or another you do end up always getting sums of pi log pi. But really the connection to the relative entropy that we're going to be discussing is at this point a little bit not sufficiently explored. There is another aspect of this which is associated to the name of Landauer, which is that information, this is his slogan, information is physical. Let's see. The idea here is that when you receive a message, the message is always going to be codified in some physical form. It's either written on a piece of paper or it's or in an electromagnetic wave, or in various ways. The information is going to be physical in the sense that it's written down somewhere. That's sort of fine. When you receive a message, there was this actual physical uh, transmission. Okay. In the same way, when you have a system, you can sort of claim that the system codifies or has information about its own state. That's the message. When you receive a system, you're essentially receiving a message. You're receiving a message about what the microstate of this system happens to be. Anyway, that's one way you can proceed here. What we're going to be doing is pursuing yet another version of what we might actually mean by information. And the idea here is we're going to be using the term information in a way that's much more closely connected to the colloquial meaning. Namely, information is what you get when your questions are answered. One advantage of this approach to information is that because you are focusing on the questions that an agent might be asking, this is much more closely connected to Bayesian approaches to probability. Very good. So what is information? Information is what you get when your questions are answered. Very good. So what we want is a notion of information that is closely connected to the way ideally rational agents behave. And so the way that we're going to handle this is to say, is in a sense by an analogy to physics, we're going to say, if you have old beliefs and you update to new beliefs, something happened that helped you or forced you to make that transition. Whatever it was that happened is what we're going to call information. Information is what allows you or forces you to update from old beliefs to new beliefs. The reason I find that this sort of picture, vague as it is at this moment, appealing, is that if you think about what happens in dynamics, in mechanics, when you have a state of motion, an initial state of motion, and something happens and the state of motion changes from an initial to a final state. Whatever happened there, this is what we're going to call a force. In fact, that's what Newton did. Force is what allows you to change from one initial state of motion to a final state of motion. The state of motion is defined by an initial probability, initial momentum here, sorry, as you make the transition to a final momentum over there. And whatever enters here is what we call force. In fact, Newton called it force, but he was really talking about impulse. And so then the concept got refined into force is the rate of change of momentum and all of that. But this is how we define what forces are. We do not need to be much more specific in order to figure out what a force might be. We only need to figure out what the effects of force are, and then we proceed. So the real genius in somebody like Newton was that he did not need to explain how it is that you have a force of gravity acting as a distance, at a distance. He would say, he actually did write that anyone who believes that such a thing can actually happen, like action at a distance, clearly has no ability in any matters philosophical, right? But once you realize that you do not need to worry about what these guys here are, you just need to know what happens to the effects of forces, you're in good shape. Similarly, here we're going to go from priors, that is what represents the old beliefs, to posteriors, that's what represents the new beliefs. The moment that we have rules for how we go from Q's to P's, we no longer need to know precisely what this information is. That's exactly what we're going to be doing. This is a very pragmatic approach. A pragmatic approach. What is information? Information is defined by its effects, by what it does. Information is what information does. It changes your mind. Okay, that's very Bayesian. But let's go here. What are the effects? One, it changes probabilities. So information induces changes of probability. But it also does something that's very crucial. Information constrains your beliefs. What I mean by that is the following. One of the things that we want to do when we do all of this is we want to be as rational as possible. It is extremely difficult. I do not know that anyone has succeeded in saying precisely what rationality consists. What does it mean to be rational? Philosophers discuss this thing all the time. It's not so easy to nail down what you mean by rationality. However, it is much easier to come up with very good examples of irrationality. One of the things that may count as being irrational is to hold beliefs that are incompatible with each other simultaneously. That's a form of irrationality that we want to avoid. You cannot both believe that it is raining and not raining at the same time. You cannot both believe that I know this is true, but I don't believe it. That's an interesting paradox, by the way. I know it's true, but I don't believe it. So how is what is the form of irrationality that we want to avoid? Well, one of them is that if you're going to consider yourself rational, you're not allowed to believe whatever you want. You're not allowed to believe whatever you want. Not everything goes. If you're going to be rational, there are going to be constraints on your beliefs. It may be still difficult to figure out what those constraints are going to be, but the existence of constraints is undeniable. You're not allowed to believe whatever you want. That's a matter of rationality. So information changes what you believe, and information constrains you to believe certain things and not others. So what we're going to actually claim here is that information is the constraints on probabilities. Let me draw a picture for that. If this is the space of all probabilities, for example, all Gaussians, or all binomials, or all multinomials, and you have a prior here, in that space, one point in that space of all probabilities, this is the space of all distributions. And then you acquire information. What is the information? The information is, look, this is your prior beliefs, or this is what you believed yesterday, and now new information is given, and the information just tells you, look, you shouldn't really believe this. You should believe something else. You should believe you should pick a probability distribution in this region. That's the information. Within this new family of probability distribution, you have to pick one. And so the question is going to be, which one do you pick? Because there are many here. But in any case, you can see that this offers you a constraint on the family of acceptable probability distributions. That's the way we're going to handle it. This constraint, this is the information. One of the things that's sort of like nice about this approach is that despite the fact that there is no measure of amount of information, we're not talking about amounts, you can still do this in a very, very quantitative way. This still allows a mathematically quantitative framework. And the reason is, you probably realize this by now, is that if you have constraints, and you're trying to come up with methods for maximizing an entropy subject to constraints, that's a very mathematical approach. So we're designing the method in such a way that the method is going to be pragmatically useful, namely you can do mathematics with it. Very good. I think that we are ready to figure out how to actually do this. We're going to take a break now, and in the next part of the lecture, we're going to come up with a method to design this updating procedure. See you then.